Hi guys, and welcome back to another reading of our book Quantum Atom Optics, Theory and Applications to Quantum Technology. So we got up to section 2.2 last time, and we didn't quite finish it because video was getting a little bit too long. So I'm going to go and finish off that section now. So let me get to the right page. Right, so basically what we were talking about there was how you get Bose-Einstein condensation, or we're basically introducing Bose and Einstein's original argument, or at least my interpretation of it. And we did this by looking at a kind of prototypical system of two-level atoms, and we weren't really looking at the spatial degrees of freedom, and we're just really looking at like considering each atom to only have 2 degrees of freedom. And so when you have many of these atoms, you know, what happens when you lower the temperature? And so we contrasted this case between the indistinguishable and distinguishable cases. And the main result was that because of the way that we count statistics for these two different cases, in the indistinguishable case, you get a much larger probability of finding an atom in the ground state. So the part that I kind of missed in last video was talking about the correspondence between these states, between this indistinguishable and distinguishable case. So just to recap, one of these states here, we would write this as like a Fock state where, say, there are k atoms in the state labeled by A, and then there's n minus k states in the other level. Okay, so hold on, let me just check that I've defined it the same way. Okay, so I've defined it slightly differently. Okay, but I think you can cope. So in this case, what I'm labeling here as K here is the number of atoms in the excited state here. So the top level I'm calling A here, and the bottom level I'm calling B. Sorry, I used slightly different notation. But these are basically the states that we're using for the indistinguishable case. And for the distinguishable case, basically the difference here is that because each atom sort of has its own identity, so we have a bunch of atoms, and each one of them can be individually in either the upper or the lower state. And so if you have this distinguishable spectrum, then for example, in the ground state, what this basically means is that all the atoms here are in this lower energy state. But if you have, if we call the lower energy state, if we call that the zero state, so for example, this state here, you would write that as, say, 0, 0, 0, 0 for 4 atoms. Now, for the first excited states, now because these are distinguishable, then any one of these atoms could potentially be in the excited state. And the difference with the indistinguishable case is that we would assign a different state according to whether it was this atom that was in the excited state, or this one, or this one, or this one. And in the indistinguishable case, that distinction just does not happen because the atoms are indistinguishable. So there's no difference really whether any of these atoms are in the excited state. The only thing that counts is that one of the atoms is in the excited state A, and then all the others are in the lower state B. So this is why there's a difference in the way that we count them. So what we're going to talk about now is basically what is the actual equivalence. So clearly this state here, where all the atoms are in the lower energy state, so this state k equals 0, we would, of course, write this as b to the power of n in factorial 0. So clearly this has a clear equivalence to this state, right? So, but then what about these states? So I've already told you that there's 5 and there's only one corresponding state here, but is there a kind of a version of this distinguishable state that we can sort of write an equivalence to, a bit like this ground state? And turns out that there is. So, for example, for that first excited state, this even superposition state, or this symmetric state, is the kind of the equivalent state of the state that you might write a dagger and then b to the 4, and then square root of 4. So these states kind of have an equivalence, and the reason why we can sort of point out this equivalence is basically because this state also has this same property of being symmetric, right? So it's a little bit like how you do first quantized notation. In order to write down this second quantized wave function in terms of the first quantized way of writing the wave function, what you do is you symmetrize over all the different potential variables of the system. And so in this case, we symmetrize the wave function in this way. And this state is kind of the equivalent state of the second quantized notation here. So of course, this is just kind of one particular state which you can form in the many superpositions of state that you can have here. So for example, if you can have some state here with some minus signs here, it would be a different state, and that would not have the same properties as this. So this is a kind of a unique state in the manifold of states that you can have in the superposition of these 5 states. So more generally, so this was just the first excited state. I'm talking about, this set of states here. What about the other excited state sectors? So for the other state sectors, then more generally, we would write this state in this way. So just to explain what this means, so this notation K, comma D, what I mean by that is this is the state with K excitations. So in other words, the number of ones here have to be equal to K. And this D is the thing that labels the degeneracy of this. So for example, here, so K would be equal to 1. Oops. So this happens sometimes for unknown reasons. So K would be equal to 1 for this. And then the multiplicity of this one will be equal to 5. And then, so for example, the next one up, K would be equal to 2 here, and then the multiplicity would be equal to 10, right? And the multiplicity, this dk, is always equal to this combinatorial factor. And I think you can easily convince yourself that it has to be combinatorics because, so for example, so if we have this, say 5 atom system. So let's make this 5 atoms. So here we go. And so the ground state 0, 0, 0, 0, 0. Now, if we have 5 atoms and then say 2 of them need to be excited, then in other words, then all the possible states that you can write down, this is just like how you learn about combinatorics in high school. You've got 2, say, so instead of, let me make one of these an excited state. Okay, so we've got 2 atoms in the excited state and then 3 in the lower state, right? Now, you can imagine them having, 5 slots like this. And then so this, if we start with putting the 2 excited state, these first 2 could go sort of anywhere, right? So we can choose here, here, or here, 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 here. And then, so basically, the number of ways that you can have two excitations within 5 is, well, the first atom, we can put it in, any five possible slots. And then the second excited state, we can put in any of the remaining slots. So it's 5 times 4. And then because for the other 3 atoms, then their locations are completely fixed. So in other words, the way that we would write this is that it would be the combinatorial factor of putting 2 atoms within 5 slots. So this, in this case, would be equal to 10. So if we just go back down here, then the number of terms in this, so basically what this is saying is that the state that has the equivalence of A to the power of K and then B to the N minus K would be equal to, has this equivalence to this particular state. And here, notice that the coefficient of here is simply just 1. So it's basically exactly like this symmetric combination. So it's just a simple sum over all these different possible states, right? So I think we should really be putting in the normalization factor here to be completely general. So I believe we should probably write it like this. Okay, so that's basically the equivalent state to the Fock states. And so I think the rest of it we covered in the last lecture. So let's now go through the exercises. So exercise 2.2.1, show using combinatorial argument that for n distinguishable two-level atoms and the number of states with k atoms, one of the excited states is n, choose k, and hence verify 2.6. So that's exactly just what we did now. So, okay, so that's fine. So let's move on to the next one, 2.2.2. So verify that 2.7 is symmetric under particle interchange. So this is the 5 qubit first excited state. So essentially, you can see that this has to be symmetric under interchange because you can choose any 2 of these qubits. So let's say we just choose the first 2, and now let's swap the ordering of the first 2 qubits. So if we swap the ordering, this one it's the same, here it's the same, here it's the same. Here, this one will become 1, 0, 0, 0, 0, and here it will be 0, 1, 0, 0, 0. And so basically what's happened is that this guy's over here and this guy's over here, and because it's an even sum of all the different terms, then basically this superposition state is intact. So it's basically unchanged. And I think you can convince yourself that it is always the case, like so. And then B, show that the state 2.7 with a minus sign on one of the terms is not symmetric under particle interchange. So 2.7. Okay, so imagine if we had a minus sign. So if we had a minus sign on one of these terms here. So imagine if this one was a minus sign, then of course, following the same argument, then under particle interchange of the first 2 qubits, this state would turn into that, and this state would turn into 0, 1, 0, 0, 0. And then if we tried to evaluate the fidelity of the original state as compared to the state with the particle interchange, what we get would be, if we just take the fidelity of this, okay, so when you take the fidelity, it's like the state compared to the reference state and then I think we've got to take the modulus squared. So then when we do this one, so we'll get a factor of 1/5, and then this is overlap of, okay, so let's just basically write it out then. So this state is unchanged, plus this state is unchanged, and this state is unchanged, and this state is like this, and then this state is like this. So when we take the, and then let's put in the 1/5. So basically this is the new state psi, and this bottom state is the reference state. And so when we take the overlap of this one and this one, we'll get 1, 2, 3, and then -1, -1. So in other words, we'll get 3 minus 2, so that's 1, and we take the square of that, so it's going to be like 1/25. So clearly the fidelity is lost. Okay, and I want to verify that 2.8 is symmetric under particle interchange. So this is almost following the definition. So any state like this, which involves K excitation. So imagine, you got a bunch of zeros and some numbers of ones, and the number of ones is equal to K. Then because this is running through all the different possible combinations, so either we will have a state where we interchange it and nothing happens, and so this will be like these terms here, or we will get situations where we interchange it and then there's a 0 and a 1, and then in this case we will basically reverse the ordering, but then that reversed ordering should also be contained under the sum, and it should have the same weight in the sum. So basically whenever you interchange it, you will kind of swap the ordering of the states in the sum, if you like, and then but if the weighting is the same, then you'll get exactly the same state. So basically it's due to that. Okay, now 2.2.3 for the full system with indistinguishable particles, probability that the state occupies the state sigma equals 0, as in the ground state, it should be equal to that according to 2.9. Yep. Okay. So this is basically saying that. Okay. So we've got a bunch of atoms here, and then the probability that it will be in, say, the ground state. This is P Pj. This is what we call Pj. Should simply be basically, because this is the probability for a single atom, and then our argument from last time was that when you have n atoms, it's basically all these atoms are acting individually, and so if it's this is the probability of one atom being in the in the ground state. You can imagine this like a rolling rolling a dice many times, and it's like, what's the probability of getting one for every single time, right? So obviously it has to be equal to P, what are we calling it here? So P, sorry, let's get the notation right. Yeah, so Pj times Pj times Pj. So, or rather possibly, this should be round 1, this should be round 2, this should be round 3, or atom number 1, atom number 2, atom number 3. So maybe I should be calling this P1, P2, P3, but actually they're exactly the same number. So I could have called just this P, if you like. So essentially the probability of this is just P to the power of n, where this P is equal to this factor. I just put the label J here because just to label it for the jth atom, but numerically they're exactly the same. Okay, so that is the probability of all the atoms being in the ground state. So this should agree directly with constructing the partition function using 2.6 and 2.4. So we should check that we basically get the same answer. So what I mean by that is, let's look at, and 2.4 is, this is the energy, considering this whole system as like one full system. Okay, so let's first write down what the energy of this state here is. So the energy of this ground state, according to 2.4, should be, so it has 0 excitations. So in other words, the energy is simply N times E0. So the energy of this should be N times E0. Okay, and then, so that was kind of the easy part. So the probability of all the atoms being in 0, so according to Boltzmann law, so it should be E to the minus N E0 times by beta. But then we have to divide by the partition function. And the partition function has to be the sum over all the possible states, so basically Z is going to be defined as the sum over all the possible states. So we can write this maybe as sum over K, sum over dk, so it's double sum, and then so the energy of, so whatever that is, K and dk, so the energy of the K dkth level times beta. And so this is our definition of Z. And then there are going to be 2 to the n terms here, because there are 2 to the n different terms in this sum. Okay, so this looks kind of a little bit messy, but there's actually a very smart way of actually working this out. And it kind of becomes apparent if I just more or less write the answer down. So that's what I'm going to do. So if we, so let me just first write the answer down and then convince you that this should be what the answer is. So this should be equal to basically the product of the individual partition functions for a single qubit to the power of n. And so this again occurs because basically the qubits are individual systems. They you don't have to consider this whole system, it doesn't possess any entanglement or anything like that. They're all separate systems. But more from a mathematical perspective, what we can do is, say if we expand this out, then we will get, for example, this to the power of n, we're going to get, for example, e to the beta times E0 times n, plus, for example, the next order term will be e to the beta e n minus 1. And then there'll be one term like this, E1. And then because when you do the binomial expansion, there are going to be N1 combinations of that, right? Because when you do a binomial expansion, there's going to be N terms that have this particular combination, right? So it's just a binomial expansion. The next order term will be N2, E be in N minus 2. And on it goes until the very last term, which is E beta. And then this is when all the atoms are in the excited state. So you can kind of see that this exactly reproduces this spectrum because it has the binomial weighting, and the energies are exactly, so if we look at the energy of, say, this first level here, it's exactly n minus 1 atoms in the energy level E0, and then 1 atom in the energy level E1. Sorry, this should be E1, and this should be two of these, sorry. Okay, so the compact way of writing it is in this way. And so if we go and basically substitute this partition function into this formula, then we recover the same relation that was proposed. So where is it? Yeah, so we said that this should be equal to p to the power of n. And so that's, of course, so we can just write that down. So it's this thing to the power of n. So this is e to the beta E0 n divided by e beta E0 plus e minus beta E1 to the power of n. So this was the first way of doing it. And our second way of doing it, which was to consider this whole spectrum, we said that the energy of that level should be n times E0, and then the partition function, I argued, should also have this form. And you can see that this has exactly the same form as that. So that's basically the answer to that one. Okay, so and finally, 2.2.4, verify that 2.11 is true for n equals infinity. So this was just this thing where we do our evaluate this sum for the indistinguishable case. So for this one, well, I guess there's a sort of a standard result. So this basically using, I guess you should know this is the geometric series. So whenever you have x to the power of k and you know, sum to infinity, then this should be 1 minus x, right? Yep. Okay. And so in other words, yeah, because this thing is on the denominator, and so when you do that sum, and basically this is a power series in k, this first term is a constant, this k is just a power series, so you can basically just use that result, and it's on the denominator, so it's 1 divided by 1 divided by x, and so it's simply 1 minus this factor here. And what is the corresponding result for any n? Okay, well, I do not remember the corresponding result for the finite series, but this is where Mathematica can help. So let's open up Mathematica and ask Mathematica what the formula is. Here we go. So if we have sum over x to the power of k, where k goes 0 to, say, n. So yes, so there's a closed form formula for this, which is equal to this, which you can use to basically generalize this result to n. But I guess the point is that for any x that is less than 1, so if we imagine n to be a very large number, then x to the power of n plus 1 is going to be very small. So to quite a good approximation, this sum converges to this, as long as x is relatively small. Okay, so I think that's all for today. And so if you enjoyed this lecture, then please don't forget to subscribe to the channel. Have any questions, and feel free to comment below, and we'll continue off section 2.3 next time. Okay, see you later. Bye.